Hello and welcome to this clip on testing for organic functional groups. We're going to be covering the common A-level chemistry tests across both year groups, year 1 and year 2, for functional groups such as alkenes, haloalkanes, carbonyls, aldehydes, primary and secondary alcohols, and carboxylic acids. And wherever I can, I'll include a filmed demonstration for each test so we can go through how to word the observations for a positive result. And in the appropriate cases, we'll look at the relevant equations or additional techniques needed to get a positive result. And finally, we'll finish off by looking at a set of short questions at the very end. So this time it's a little bit more involved. The positive observation is a precipitate being formed after the addition of ethanol, warming, and adding dilute AgNO3. And just making a quick correction there, I should have said nucleophilic substitution of OH minus, not just OH, onto the haloalkane. So it's a hydrolysis reaction as well. So I've set up the necessary water bath and a fume hood to provide the warming, because obviously just using hot water from the tap instead of water heated using a Bunsen burner is a bit safer. So I've labelled up my test tubes, and the first one I'm going to do is bromobutane, which you can see from the equation at the bottom of the screen. So you can see clearly that the temperature of the water bath is between 40 and 50 degrees C. So adding a little bit of chlorobutane to the test tube. Rearrange everything so you can see which test tube is which. So to the test tube, next one, I add some bromobutane, one bromobutane. So obviously what you'd be doing here is if you're writing the equations, you just put Br instead of Cl, Br minus instead of Cl minus. So thirdly, finally, one iodobutane, C4H9Y. So now we add some ethanol. And the ethanol has the role of a solvent. So remembering that haloalkanes are insoluble in water, so therefore what we need is something that can dissolve, or allow the haloalkane and the aqueous solution to mix, because the water is what's actually behaving as a nucleophile. So the water that the silver nitrate solution is dissolved in acts as the nucleophile. So it's not actually, as some people sometimes think, mistakenly, that it's the OH minus ethanol. The ethanol doesn't actually dissociate into OH minus and part of the molecule. What it does is allows the haloalkane and the water to mix properly. So now we put them into water bath and we add the silver nitrate. And the silver nitrate has the water in it. Aqueous. And it also contains silver plus, Ag plus, in the equation at the top of the screen. So we add a few drops to each haloalkane. You should be able to see in a minute, when we take the test tubes out, the formation of precipitates. Look at the iodide, you can see a yellow precipitate of silver iodide. Look at the bromoalkane, you can see just the beginnings of the formation of the precipitate there, sort of whitish cream colour. And the chloride doesn't appear to have formed a precipitate yet. reason we can't see the silver chloride precipitate at this point is it's got the highest bond enthalpy of all the carbon hydrogen bonds here. So the other two carbon hydrogen bonds, the carbon iodine and the carbon bromine bond, go more quickly because they have a lower bond enthalpy than the carbon chlorine bond. See clearly the formation of silver bromide precipitate and the formation of the silver iodide precipitate. So, if we have a quick look at the different carbon halogen bonds that are present, we can see that there's an increasing rate of hydrolysis due to a lower bond enthalpy going from left to right. So what I've got on this one is the mechanism and the typical equation. We're going to use cyclohexene as our alkene. You can see in the photographs, which I'm going to turn into videos in a second, that we've got bromine water and cyclohexene on one side, and bromine water, and we're going to test it with cyclohexane on the other side. So I'm going to play both clips together, and we're going to look for bromine water being decolorized from orange to colorless via an electrophilic addition mechanism. So on the left hand side we have the cyclohexene being added to a test tube, right hand side of the cyclohexane being added to a test tube. So now what we've got is on both sides we've got cyclohexene, and on the other side we've got cyclohexane. So just following the left hand side first, bromine water to cyclohexene, and it decolorizes. And simultaneously I was adding bromine to cyclohexane on the right. You can see one decolorizes and one does not. So to perform the same test on the tube on the right, which I'm holding in the hand, is the same as the tube in the left hand video. See once more the addition of bromine causes decolorization of bromine because the cyclohexene reacts with it. Add a bit more, greater quantity, just to check that that's happening. And we can confirm it once more. So in this first clip, I've deliberately left out the acid so you can see the importance of it. So I'm proceeding as if I've forgotten. I've checked the temperature of my water bath, it's between 45 and 50 degrees. Take my ethanol and I add it to a small amount to a test tube. And I've got my dichromate just in there behind the beaker, where I'm wearing gloves just to make sure that my hands are stopped or prevented from coming into contact directly with the dichromate because it's toxic. I'll add a small amount to the test tube. So you can see the colourless alcohol. Add a little bit of dichromate to it. Now it's being warmed up in the water bath. Remember, the dichromate hasn't been acidified, so if you look at the oxidizing agent equation, you can probably guess which part is not present. And we're sitting here waiting for it to start changing colour. I'm deliberately continuing to film because you can then see that there's little, if any, colour change whatsoever. So nothing happens. So now let's do it with the acid. So in this second clip we're picking up where we left off. I'm adding some sulfuric acid directly to the reaction mixture this time. So keep an eye on the colour of the reaction mixture, and in the background keep an eye on the colour of the dichromate. So we've added our sulfuric acid. Hopefully give it a few seconds and it should start to change. Give it a bit of a shake to get it moving. Normally what we do is we pre-prepare the dichromate by adding the acid to the dichromate before we add the dichromate to the reaction mixture. But hopefully you're starting to spot that there's a change happening. You can see a slight darkening of the reaction mixture in the test tube. So when that's proceeded sufficiently, what I'll do is I'll show you up close the two different colours. So looking at the orange that you started with in the bottle, you can see clearly now that it's starting to turn to green. So if I get the bottle of dichromate, it's clearly still orange, but the reaction mixture has gone green, so we have a positive test result this time. So before we go any further with carbonyls, it's worth just pointing out that the actual term carbonyl, although we use it quite a lot when referring to the C double bond O group within a molecule, it's really only used to describe compounds that have this particular group bonded only to another carbon atom or hydrogen. So true carbonyl compounds which respond positively to the carbonyls test that we're going to look at are only aldehydes or ketones. So there's actually two tests we're going to look at for carbonyls. The first one is specifically for aldehydes, and the second one is only works for aldehydes or ketones, but no other C double bond O containing groups or compounds. So the first one, with Tollen's test, what you've got to do is actually make the Tollen's reagent to start with. So you start off by adding some ammonia dropwise to aqueous silver nitrate with a few drops of 0.4 molar NaOH solution added. And you keep adding the ammonia until the brown precipitate just starts to appear. This is silver 1 oxide. So what happens after this is you have to continue adding the ammonia until this precipitate disappears. There'll be a photograph of that coming up in a second. So we now have Tollen's reagent, which contains a linear silver 1 diamine complex. It's a little bit outside the specification, but it doesn't matter because it's an interesting, just side note, that it's a linear complex as opposed to octahedral or square planar, etc. And it's two ammonia ligands bonded coordinately to a central silver plus ion. So this is the active ingredient in Tollen's reagent. And the next thing to do is to take this test tube and put it into a water bath in a fume hood to warm it up. And if we now add some propanol or an aldehyde to that mixture, you'll slowly start to see a silver mirror forming. It takes a couple of minutes, sometimes up to 5 minutes, so I've done this particular part of the clip in photographs instead so you can see the relevant parts. So hopefully you can see on the test tube, on the inside of the glass, you're starting to get some silver forming. So what's happening here is that the silver is being reduced, silver plus is being reduced rather, I should say, to silver metal, as indicated by the equations in blue. So this is the positive result you're expecting to see to confirm the presence of the aldehyde functional group. So now let's move over to the 2,4-DNP test for aldehydes and ketones. So with this particular test, you add 2,4-dinitrophenylhydrazine to a warm sample of your compound, looking for a positive test result of an orange precipitate. This orange precipitate will be a 2,4-dinitrophenylhydrazone derivative of your aldehyde or ketone. An example is given in the equation at the bottom of the screen. And you follow this up by recrystallizing your derivative using a minimum amount of hot solvent and then filter under reduced pressure. After this, you determine the melting point and compare with the database for the 2,4-dinitrophenylhydrazone derivative to get a positive ID on your original compound. So we start by assembling all of our materials in the fume hood. All the compounds we're talking about are toxic and flammable to some degree or another. So particularly the 2,4-DNP, it's very toxic indeed, so you have to wear gloves when you're using it. It's actually a common precautionary use with many organic compounds. The safest thing to do is to assume that they're dangerous to come into skin contact with, so you just wear gloves automatically as well as your lab coat and your goggles. So the next thing to do is to show the precipitate you're looking for. So in the final picture you've got the 2,4-dinitrophenol hydrazone precipitates. Now obviously the purification process for these is slightly outside the scope of this particular clip. I have another clip on organic solid purification. I think it's called organic synthesis techniques or something like that. But it's worth remembering that these are now crude products and therefore need further purification. The details of this further purification would be in the follow-up technique part of the screen. So you recrystallize these under minimum or using minimum amount of hot solvent, usually ethanol works quite well, and then filter them under reduced pressure using a Buckner funnel, and then determine the melting point comparing this with the database for the 2,4-dinitrophenol hydrazone derivatives. So the next screen is going to show you such a database. So you can see there's information here about the melting point of the 2,4-dinitrophenol hydrazone derivatives. So what you do is you test your melting point of your purified solid, your 2,4-dinitrophenol hydrazone derivative, and check it against a database. So we've got some ketones here you can have a little look at. Similar types of ideas there as well. I should point out that this actually isn't my personal database, it's just one I've pulled off the internet. So I'm not taking credit for it at all. But it's worth just referring to one. You can either look at it online or you can have a data book perhaps. But either way, the idea of referring to a database is really important if you're answering questions on this. So when we're testing for carboxylic acids, we're testing for the COOH group. And basically what's happening is COOH dissociates into H plus and A minus. So that's where the H plus in the equations comes from. It's the dissociation of the carboxylic acid. So I've got a little short excerpt of a clip of me doing this one, so I'm just going to pop that on there now for you. So this first one I did using quite dilute ethanoic acid, 0.1 moles per decimeter to -3. You can see it on the label there. So even using a reasonably concentrated 1 mole per decimeter to -3 sodium carbonate, when we added it, I'm not sure if you'll be able to see the fizzing. It wasn't very strong. A little bit of fizzing, maybe perhaps just to start with, but I felt that wasn't very indicative perhaps of what we're trying to demonstrate here, so I actually did a second clip where I added some solid sodium carbonate instead. Now in the top of the screen you'll see it says add aqueous Na2CO3 or aqueous sodium hydrogen carbonate. You should be able to make it work with aqueous solution. So I gave it another go to try and make it work this time using solid sodium carbonate. So it's the same ethanoic acid, put it in a fresh test tube, and take a bit of sodium carbonate out and just pop it straight into the test tube to see what happens. So it's the same sodium carbonate that the solution was made out of. So rather than go and make up some brand new ethanoic acid, just use some solid acid. And hopefully you can hear the fizzing and see the bubbles. So positive test result this time, effervescence due to the carbon dioxide gas being given off. Okay, so now it's time to perhaps have a look at some exam style questions which may pop something into them about testing for functional groups. It's actually quite unusual to find a functional group testing question that's just about the test itself. It's usually popped in there like a 2 mark or 3 mark or maybe a 1 marker as part of a bigger organic style question. There might be a bit of mole calculations in there, there might be a bit of mechanism stuff in there. So I've taken the questions as they are, so that hopefully you'll see the context I'm talking about when we have a look at it in a second. So before we look at any of the exam style questions, it might be worth pausing the clip and getting all of these tests down on a piece of paper or maybe each test on a separate flashcard so you can go away and learn them a little bit later. So what I've done is, where it's not necessary to know the equations or to know the type of reaction perhaps, or anything, or the mechanism indeed, I've just put not applicable or N/A. But all the other bits and pieces that are included, they would be on any of the A-level chemistry syllabuses that are out there at the moment. So, if you want to pause the clip now, that would be a good idea, or maybe you want to come back to it, but the next thing we're going to do is to have a look at some exam-style questions from past papers. So this question is about alcohols, and it gives you a little bit of a description of a reaction with some data and some information about what's being added and what sort of reagents are being used. And they start off by asking the molecular formula. So that's just a basic idea of adding up all of the carbons, the hydrogens and the oxygens, a little bit like a shopping list. So C4H10O would be appropriate for the molecular formula because it's literally just the number of atoms of each element present. When you write a balanced equation, I'd recommend maybe switching over to structural formula here, because then that gives a little bit more detail about the functional groups that are involved, and the examiner likes to see that you know what functional groups are involved. So what I mean by that is change it over to C4H9OH. So that's your reaction, obviously. Now we can go down and have a little look at the data. So it asks you to use the data in the table below to answer the questions that follow. So it gives you density. So looking at the values, you can see quite clearly that water has a greater density than either 2-methylpropan-2-ol or 2-chloro-2-methylpropane. So therefore the upper layer is going to contain the organic product. So your reasoning is that water is more dense than either of the organic compounds that are present. So the organic layer was shaken with a dilute solution of sodium hydrogen carbonate. We just looked at that, haven't we? And a gas was given off, and they want you to identify the gas. Obviously we now know that would be carbon dioxide. And the chemical that could have reacted with the NaHCO3. So let's have a look back at the question a bit further up. So we've obviously got HCl. Whoops, sorry. There we go, HCl. So we know that, sorry about this, we know that carbonates and hydrogen carbonates react with acids. So this time it's not a carboxylic acid, but it is an acid. And carboxylic acids are no different. So just putting this into the context of what we were talking about a few moments ago. So let's go on to the next part of the question. So let's now go to the next part of the question. We've got to move back up to the top and shift it over a little bit like that. So the resulting impure organic liquid was dried with anhydrous calcium chloride and then distilled, and 3.75 grams of pure 2-chloro-2-methylpropane was produced. So it asks you at what temperature do you expect the pure organic product to distill. So your organic product is 2-chloro-2-methylpropane. So let's go and look at our data. Just moving it over. 2-chloro-2-methylpropane is 51 degrees Celsius, so we can move the page over again and put in 51 degrees. So this next part obviously shifts over to an emphasis on calculation. So how many moles of 2-methylpropan-2-ol were used? So let's start with that. So the first thing to do is to check the MR and write it out. That gets you a mark. And now what we can do is go and have another look at the beginning part of the question to see how many grams we were using. So it shows quite clearly 4 grams, top right hand corner of the screen. So now we need to go and use that to calculate the number of moles that will be present in that amount. That gives us 0.054 moles. Then it asks us to do the same thing, how many moles of pure 2-chloro-2-methylpropane were produced. Now we've got the mass of that particular compound produced on this particular page, so now we can just go straight in and do the same idea. So this new compound works out as 92.5 grams per mole, so you actually physically put that down in your answer. So that gives you 0.04 moles. So now we can go down to the next part, which is to calculate the percentage yield. So remembering from the equation that the mole ratio of the two compounds is 1 to 1, the percentage yield is actual yield over theoretical yield, both in moles, times 100. Now I'm just pausing here because I need to make a little self-correction as I go. This one here, 3 significant figures. This one here should be 3 significant figures. So I've been a little bit naughty, and I'm going to go back and correct what I've done. There you go, see, I'm a good boy, me. So now what we can do is we can stick in the correct number of significant figures. So that gives us 75.9%. I've even managed to put in a little winky face for you. Right then, moving swiftly on, I need to get back on track here, don't I, really? The next question. This is again talking about an application of, it looks like it's a rather complicated looking carboxylic acid, because it says 2-ethyl 3-methyl butanoic acid. So then it says that the 2-ethyl 3-methyl butanoic acid can be made by oxidizing an alcohol. I'm not going to read them out because you can clearly read it for yourself. State the reagents and conditions that could be used for this oxidation. Describe what colour change you would see. This is straight out of what we looked at earlier, isn't it? So we can rattle this off quite quickly. So now it asks us to state with a reason whether a reflux or distillation apparatus should be used to produce the correct oxidation product. So that's quite straightforward. It's not actually testing for functional groups as such. It's really just realising that aldehydes would be made by distillation and carboxylic acids would be made by refluxing. So we're going to go for reflux, and we just give a little bit of reasoning that complete oxidation would occur. Now, how did we work out that this particular compound, 2-ethyl 3-methyl butane 1-ol, was a primary alcohol? In other words, it would oxidize via the aldehyde. What you do is you look for CH2OH in the structure, so it's a bit of a shortcut. It means you don't have to draw out the whole thing to work it out. But you do have to visualize it, because the next thing that they want you to do is to do the molecular formula of 2-ethyl 3-methyl butane 1-ol. So what you could do here is draw out the structure on the side, just to remind yourself what it would look like. So this would get us C7H16O. So let's move the screen down so we can see what the next part of the question wants us to do. They want you to write out the equation for representing the oxidizing agent. So you'll notice there was a bit of testing for alcohols here, and there was also writing out the equation for what is actually happening. So don't forget we have to use O in square brackets as our oxidizing agent. So notice that it says for this oxidation, I've switched here to using structural formulae to show the functional group changes. So although you don't have to sort of write in, use structural formulae for functional groups, obviously in your question, I've just chosen the opportunity to illustrate the idea a little bit. If you just happen to have ordinary molecular formula, you wouldn't be able to clearly show the examiner that you understand what functional group changes are taking place. So remembering that earlier on we'd recognized that the alcohol is oxidized via an aldehyde, looking further up on the screen, this second to last part says identify a likely organic impurity which could be formed in this oxidation. So we're looking at 2-ethyl 3-methyl butanal, which is the aldehyde that's being referred to by word up in the answer towards the top of the screen. So finally it says if 2-ethyl 3-methyl butane 1-ol were replaced by 2-ethyl-3-methyl-butane-2-ol, oxidation would not occur in this experiment. This is now remembering that oxidation of alcohols doesn't necessarily always include tertiary alcohols, particularly if you're looking at K2Cr2O7 in the presence of acid. So you need to say that 2-ethyl-3-methyl-butane-2-ol is a tertiary alcohol, step 1 or point 1, which wouldn't oxidize under these conditions, which is K2Cr2O7 in the presence of H+. So let's go on to the final question now. Then it says alkenes can be oxidized to give carbonyl compounds, and this reaction breaks down the carbon chain at the CC double bond as shown in the example below. So this is obviously an applied question because this reaction is not on any A-level syllabuses, but they're giving a little bit of information to you and getting you to deduce something from it. So you can see clearly that you've now got carbonyl compounds because you have C double bond O bonded directly to either carbon or hydrogen but nothing else. So it says outline a test you could carry out in the lab to show that the carbonyl compounds produced in this reaction are aldehydes. So the first thing you do is you warm it with Tollens reagent. Very important to say that you warm it, don't just say Tollens reagent. And then it says describe a non-spectroscopic method. Now we've done a demonstration of this non-spectroscopic method in this clip. It's obviously 2,4-DNP. So let's move the page down to enable us to fill that part of the question out. So firstly you add it to 2,4-DNP. You recrystallize the precipitate formed and then obtain the melting point and compare it to a database of known melting points of 2,4-DNP derivatives. So I said 3 things to match the 3 marks that were available. So let's now move the page a bit further down. And it says identify the products you would expect if you had pent-1-ene and 2-methyl-but-2-ene. So what we need to do is have a look at what's actually going on. So it looks like the carbon-carbon double bond is broken and carbonyl is produced, or 2 carbonyls are produced. So you split the carbon double bond in half. So a bit of deduction is needed first before you try and dive in. So now what we do is we take pent-1-ene and draw that out. So that gives us methanol and butanol. Drew out the structures so you could see what I meant. Do the same now for 2-methyl-but-2-ene. Applying the same idea, that gives us those 2 structures, which are of course propanone and ethanol. So let's now go on to the next page where the next part of the question is. So you just have to move the page over. And now it says an unknown cycloalkene with molecular formula C7H12 was oxidized using the method above. The only organic product was 2-methyl-hexane 1,6-diol. So they want the structure of 2-methyl-hexane 1,6-diol. Or diol, sorry. So start with your main carbon chain, hexane. A diol means 2 aldehyde groups. The 2-methyl part, that can come in anywhere you want, it can be from either end. And of course you need to populate it with hydrogens as well. So, the final part is actually quite challenging. It says identify the cycloalkene. So to think your way through this, the idea that 2 aldehyde groups, 1 on each end of your molecule at the top of the screen, originally came from a carbon-carbon double bond on a ring structure. So we've got to think about that a little bit laterally here. You can take the long carbon chain and wrap it round in itself like a ring. And by doing that, you create a cycloalkene. Be careful because you've got a methyl group. Now the methyl group is situated 1 carbon away from the one of the aldehydes. It's on carbon number 2. So seeing as the aldehydes were the source of the carbon-carbon double bond was the source of where the aldehydes occurred, it must mean that it's this particular structure, which is 2-methyl-cyclohexene. Okay, so hopefully this was a reasonably useful clip, and you could see the way in which they had put organic functional group tests into slightly larger exam questions. I felt it was important perhaps to go through a few exam questions where the context wasn't always about organic functional group tests, but you could see how they might fit it in as a 1 mark here or a 2 mark there. Okay, so once again, thanks for your time, and hopefully see you soon.